All right, now it's all about practice time. Once we've done this, you're going to come and you're going to do some more questions. I'm going to practice all of these to make sure we've got them down pat. All right, so we're going to look at molecules. We're going to decide whether or not they have the two things we need. Do they have a difference in electronegativity, and are they asymmetrical? So to begin with, let's go back and think about our periodic trends. The first periodic trend we've got is the we're going to need to think about electronegativity in its trend. So that means that as you go from bottom to top and from left to right along your periodic table, your electronegativity is going to increase. So think about this guy over here. That's fluorine. Fluorine always has the highest electronegativity. We've also got next to fluorine, you've got a couple of others. You've got oxygen, you've got nitrogen. They're nice and electronegative. And then hydrogen as well. Hydrogen we're going to come back to its bonding as well later on, but it's a bit special. So to begin with, we're going to go through all of these molecules. So all of these molecules are in your notes. They're after the picture, this picture here. So let's have a look at this. Are the bonds polar? Does that mean, is there a difference in electronegativity between one and the other? So if you need to pause and get yourself up an electronegativity table, do that now. Magic, here I go. All right, so to figure out whether or not the bonds are polar, what do we need? We need an electronegativity table. You can always just go, are they the same? Yeah, if the molecules are the same, then yes, there's no difference. Sorry, there's no difference in electronegativity if they're the same. These ones are different, so it's likely that they're polar, but let's have a look and just check how polar they are. So let's go to our table here and we go to the electronegativity of carbon. Up the top here is 2.55 and oxygen is 3.44. So heading back to our diagram here, we go 2.55 electronegativity and this one is 3.44. 3.44. Yeah, and because there's a difference, because there's a difference, we say yes, the bonds are polar. Now, is the molecule asymmetrical? If you cut it down like this, yeah, down the middle, is it different on this side and this side? No, it's not different at the moment, so that one doesn't work. That's still symmetrical. So let's try the other plane. So we'll cut it this way, and it still looks the same on both sides. So the problem with this molecule now is the bonds are polar, but the molecule is not asymmetrical. So therefore, we say that this molecule is non-polar. All right, so let's have a look here. This is a compound called formaldehyde. So formaldehyde, are the bonds polar? We can go back and we can check them up again. This one was 2.55. This one was 3.44. Okay, let's just have a quick look. Hydrogen is 2.2. 2.2. 2.2. So are the bonds polar? I would say, hell yes, they are. There's a difference in electronegativity. Is the molecule asymmetrical? If you cut it down this plane, then no, it's not. However, if you cut it this way, this bit here is different to this bit. So therefore, I would say yes, the bonds are polar. Yes, the molecule is asymmetrical. And so therefore, this molecule should be identified as being polar. Okay, so it says right down the bottom in your notes here on the next page, it talks about formaldehyde and water. So formaldehyde and water have the charge asymmetrically distributed across the molecule. We can see here that it's asymmetrical. Therefore, they're polar. Polar molecules will attract each other with the negative dipole of one molecule attracting the positive dipole of the other. So if we think back to what we've got here, this charge had a 2.2, we had a 2.55, and we had a 3.44 up here. So what we're looking at is that this part of the molecule is going to be negative, this part of the molecule is going to be positive. Okay, so that might help us just when we're figuring out that. So let's have a look at water. Again, there's a difference in electronegativity. I'm not going to write them down. So yes, the bonds are polar. Is the molecule asymmetrical? Yes, because if you cut it this way, it's definitely heavy on the bottom compared to the top. If you cut it that way, it's not, but that doesn't matter because you've got to cut it in both planes. So yes, the bonds are polar. Yes, it's asymmetrical. So therefore, we say that this molecule is polar and undergoes dipole-dipole attraction. All right, this is a bit tricky. It's showing kind of three-dimensional shape of methane. So are the bonds polar? There's a difference in electronegativity. Remember, this one is, this one is, I've now forgotten. I'm pretty sure it's 2.55. This one's 2.2. So yes, the bonds are polar. They're quite weak, but they're still polar. But is it symmetrical? So to do this, I'm going to need to get you a model. And here's one I prepared earlier. Okay, so here's my model of methane. So let's think about it. If I was to cut it down this plane, it would look like that, yeah? And same on both sides. I can keep rotating it and I can see that that would be the same. If I cut it down this plane, look, it looks the same. What about if I cut it down this plane? Look, it looks the same. So what we actually see is even though this one is a three-dimensional molecule, it's completely symmetrical. If you were to cut it in half in any direction, you would end up with the same on both sides. So no, it's not asymmetrical, and therefore it's non-polar molecule. Okay, so all four molecules, and this is have polar covalent bonds, but carbon dioxide and methane are symmetrical, and so therefore carbon dioxide is sorry, this is not carbon dioxide. Yeah, this one is methane. So methane is nonpolar, carbon dioxide is nonpolar, but these two in the middle here, because they have that asymmetry, that makes them polar. All right, so this diagram here, we're now on that next page and you can see them. This diagram represents solid hydrochloric acid. Oh, you still can't see it. Let's try and get there. All right. This is the diagram I was talking about. So this diagram here shows, smaller. Right. This diagram here is showing solid hydrochloric acid. Now the intermolecular bonding here, because you've got a difference in electronegativity, these are polar molecules. So polar molecule, and therefore this interaction here is called dipole-dipole. What's the other interaction that's happening here? Plus dispersion forces. So both of them are happening at the same time. And that is the end of my example. Now, it's really, really important that you practice these. So we've now finished 13 pages of this booklet. I really need you to make sure that you go and you complete the questions on 7.2. All right, so you're going to stop, and by the end of this week, I want us to have 6.2, 7.1, and 7.2 completely done. All right, but otherwise, you've done a really great job, and I'll see you next time.